When you think of your brain, you might think of chemical reactions and electrical signals taking place, which you might think generate all your thoughts, dreams, and your consciousness. If this is the case, your mental processes should be explained fully by classical physics. However, the way we think and operate seems to be completely different from how classical physics operates at the macro level. And a new field of research called quantum mind theory is challenging these established beliefs that we're nothing but biological robots determined by the laws of physics. In the past few decades, a new field of research has begun called quantum biology, which is the field of science that applies quantum mechanics to biological systems in order to explain how they operate, where classical biology cannot give a full account. Several aspects of biology cannot be explained by classical biology alone, and quantum biology is providing better models for biological systems. For example, quantum mechanics has been shown to play a role in photosynthesis, and seems to be utilized in how birds migrate. Quantum mechanics might also play a role in how we're able to smell. Quantum entanglement has been shown to hold together DNA, and researchers recently found evidence of quantum jitters within our DNA, which could be a driving force in evolution.
Duke researchers have found what they call quantum jitters in the shapes of DNA bases that may account for the spontaneous mutations driving both evolution and disease.
It was once argued quantum mechanics played no role in macro objects, let alone biological structures, because the environment was too hazardous for quantum processes. But this research refutes this claim. It is now known biological systems can and do take advantage of quantum processes and use them for beneficial means. When our modern theory of quantum mechanics was first developed, some physicists speculated it could possibly explain another conundrum: life and consciousness. One of the reasons was quantum mechanics was confirmed in multiple experiments, and the strange rules of the quantum world seemed counterintuitive. So some suggested it might unlock a completely new way of looking at the world that could eventually lead to understanding the rules and features of life. This was seen as speculative at first, but recently, new evidence has supported this idea. About a decade ago, the physicist Friedrich Hertz began suggesting the mathematics of quantum mechanics could be used to model the inner world of the mind. We point out that quantum mechanical principles, such as superposition and interference, are at the origin of specific effects in cognition related to concept combinations. We investigate the implications of our quantum modeling scheme for the structure of human thought and show the presence of a two-layered structure consisting of a classical logical layer and a quantum conceptual layer. In other words, the inner world of the mind seems to act as if it's quantum-like. For example, in quantum mechanics there's something called a superposition, where a quantum system can behave as if it's in multiple states at the same time, until it's measured, and a collapse happens to the final observable position. However, Hertz notes this seems to be how our thoughts behave. We often can have multiple contradictory ideas or solutions to a problem existing in our mind simultaneously, before we consciously cause collapse to the final decision that we carry out in our classical or macro reality. Sometimes it feels like certain thoughts or memories are entangled. You might be thinking of one subject, and instantly you're connected to another subject that just popped into your mind. We can also think of mental processes like quantum tunneling. For example, you may encounter an odd object or smell something that instantly reminds you of a long-lost memory. And we can bounce around between different topics without any logical path from one to another. Hertz suggests these concepts and more are better at explaining how the mind operates. In other words, the mind seems to behave in a quantum-like manner, and mental processes can be modeled as such. It has been argued this is nothing more than a coincidence, that the brain is just a classical machine that behaves quantum-like when generating the mind. In fact, it is fair to say many researchers working on quantum cognition speak of it as merely an abstract framework for modeling the human mental lexicon through the brain's network of neurons. But this element alone is probably not enough to fully explain why the mind acts quantum-like. And one could argue the brain's neural network is somewhat of a reflection of an underlying quantum mechanical aspect deep within the brain. And from computational issues alone, it is unlikely the brain just simulates a quantum system. It makes more sense from a biological standpoint to just utilize quantum processes instead of simulating them classically. And we know biological processes can and do utilize quantum mechanics. Stuart Hameroff explains.
So quantum cognition is this mathematical approach, and from Wikipedia they say, well, the field clearly distinguishes itself from the quantum mind, as it is not reliant on the hypothesis that there is something quantum mechanical about the brain. So they're trying to have their cake and eat it too. They're trying to say we're using quantum mathematics, but we don't want to go on that risky limb that there's quantum biology in the brain, because everybody knows the brain's too warm, wet, and noisy to have quantum computing going on. Nonetheless, some of us do feel that the brain has quantum biology, and it has to. And for example, if a classical system would try to simulate a quantum system, you'd have exponential slowdown, as Feynman showed. It would be, you wouldn't be able to do it. It would involve so much computation. And what would be the point of using a classical system in the brain to simulate a quantum system if you could have the quantum system?
Furthermore, we do have evidence quantum processes seem to exist deep within the brain. Physicist Matthew Fisher brought to light a study from the 1980s where mice were given either lithium-6 or lithium-7 and compared with a control group. Lithium-7 is used in pharmaceutical drugs to treat things like depression or bipolar disorder. Now, if the brain is purely chemical and not quantum, lithium-6 should have the same effect. The reason is, chemically, they are the same, as they have the same number of electrons. The only difference is, lithium-7 has one additional neutron in the nucleus. So the only difference is their quantum vibration frequency, not their chemical makeup. However, researchers found vast behavioral differences between the lithium-7 group and the lithium-6 group. The lithium-7 group mellowed out and displayed little interest in performing normal, instinctual tasks, and the lithium-6 group had the exact opposite effect. Fisher says, for the mother rats fed lithium-6, their nest building was reported to be excessive. Nursing was very frequent, long duration. Grooming and retrieval of pups was excessive. So these were the cleanest and safest rat pups in the world. State of alertness, instead of being average or low, was reported to be very high. Apparently, not only did lithium-6 and lithium-7 have different effects on the mood of the mother rats, but the effects had opposite sign. Thus, the change was influenced by the resonance of the quantum particles, not their chemical makeup, implying there are quantum processes in the brain that correlate to our mental properties. Quantum cognition seems to be more than just a model.
So let me just assume this experiment is right and ask, how on earth could this possibly be that the two isotopes of lithium have an opposite effect on the sign of the mood of these female rats? Well, okay, there's a mass ratio of 7:6, not so big, but what's remarkable is the nuclear spin entanglement time. I showed you this 10 seconds. Well, it turns out that's for lithium-7. Lithium-6 is 5 minutes. I don't know about you, but my memory is not much longer than 5 minutes. And when I saw that, I was like, good Lord, could it really be that evolution had, undergone the process where nuclear spins, became qubits in a quantum processing in the brain, and that our brains are some sort of quantum computer?
Other research has only supported the notion the brain is actually quantum computing. Within the past few years, additional research has been published supporting quantum mind theory. Information processing has been reported to be taking place within microtubules, where quantum mind theories say quantum processes are taking place. Another paper has shown that tubulin protein molecules will self-assemble via quantum tunneling. On top of this, we even have evidence that suggests quantum vibrations are coming from microtubules, which would imply topological qubits are likely within the brain. Quantum biology researcher Bandiopadhyay, said the microtubule appears to be a fundamental information processing device in biology. Thus, it appears we have sufficient evidence quantum processes are taking place within the brain. Most of these theories for quantum mind revolve around the basic premise that deep inside neurons, there are tiny structures called microtubules, which are made of proteins called tubulins. Since tubulins are proteins, they contain amino acids called tryptophan. On a molecular level, tryptophan at its end is made up of 6 carbons bound together in the form of a ring. The ring contains electrons that oscillate from one side to the other. Because of the uncertainty principle in quantum mechanics, the actual location of these electrons is more properly described by a wave function or as a cloud of possible locations. Because these tryptophan molecules are close to each other, one tryptophan ring can share an electron cloud with another tryptophan ring. Sharing of the electron clouds causes the displacement of the tryptophan into a superposition of 2 states. So basically, all this means in a nutshell is, according to quantum mind theory, within microtubules of a neuron, due to the molecular makeup of tubulins, they can exist in a superposition of 2 states, which we'll represent as a 1 or a 0. Being in a superposition, it would exist as both a state of 1 and 0, which would be known as a qubit, until it collapses to one state or the other. Now, since tubulins make up microtubules, the sharing of the superposition along an electron cloud can exist along several different pathways, which is known as a topological qubit. Thus, through the different possibilities of just one microtubule, different pathways could exist in a superposition, and this results in large-scale coherence among thousands of tryptophan molecules on a microtubule. Now, here's where quantum computation comes in. The 2 requirements for quantum computation are a superposition of 2 states, which allows molecules to represent qubits, such as a 1 and a 0. We have seen how this can occur in just one tryptophan molecule, which when displaced exists as a superposition of a 1 and a 0 state. The second requirement for quantum computation is large-scale coherence. Again, we have seen how this can occur among thousands of tryptophan molecules. Thus, microtubules inside neurons could potentially fulfill the 2 requirements necessary for quantum computation. Now, I know this is a little complex, but what this would mean is the brain could compute different possibilities simultaneously until a decision is made by the agent and a collapse to one state is produced, which corresponds to the intuitive way of how we think, as well as what researchers found in developing the model of quantum cognition. This is also supported by the fact that there's a correlation between the binding affinity of many brain-altering chemicals, like anesthetics, for the hydrophobic pockets where these tryptophan residues are located and their anesthetic potency. In other words, the more tightly an anesthetic binds to tryptophan residues on microtubules, the more likely they are to disrupt cognitive processes like memory formation, suggesting there is a correlation between microtubules and how the mind interacts with or manifests as the brain. When these theories first came out, some claimed the brain is too large and wet for quantum coherence. What this means is the brain contains a lot of water, and the random motion of water seems to destroy quantum coherence and produce decoherence, and thus it was claimed the brain is too wet for quantum computation to occur. But these objections don't work for 3 reasons. First, the objection is based on a mathematical miscalculation, assuming the superposition needed to be much larger than what quantum mind models predicted. And since the superposition would be much smaller, there would be less of a chance for interference. Second, the tryptophan molecules, which were proposed to be involved in quantum coherence, exist in areas of microtubules which are hydrophobic. That is, areas which exclude water and would protect against interference. So water molecules cannot enter into these areas and interfere with coherence. Third, this objection was directly challenged by the fact that quantum coherence does seem to play a role in biological organisms, as we discussed earlier. These biological organisms contain as much water as the human brain, and that doesn't seem to preclude quantum coherence from taking place. Quantum mind theory also deals with another objection from physicalists and explains how the mind can cause collapse within microtubules. Physicalists have argued a non-material force such as a mind could not influence the brain, as it would violate the law of conservation of energy, which states the total energy of an isolated system remains constant. If another force was acting upon our brains, that would require some type of outside energy source and violate the law of conservation. But neuroscientist John Eccles and physicist Henry Margenau responded to this by appealing to quantum mechanics. Some fields, such as the probability field of quantum mechanics, carry neither energy nor matter. In other words, if the mind behaves or manifests as a quantum process, it could cause collapse of the brain without violating the law of conservation, by simply affecting the probability outcome within the brain, instead of through a process of adding energy. Margenau says, in very complicated physical systems, such as the brain, the neurons and sense organs, whose constituents are small enough to be governed by probabilistic quantum laws, the physical organ is always poised for a multitude of possible changes, each with a definite probability. If one change takes place that requires energy, or more or less energy than another, the intricate organism furnishes it automatically. Hence, even if the mind has anything to do with the change, that is, if there is a mind-body interaction, the mind would not be called upon to furnish energy. So John Eccles concludes in citing Margenau, the law of conservation is not violated if the mind manifests and behaves like a quantum process, which would be expected given the recently discovered evidence for quantum mind theory. The quantum nature of the mind suggests it doesn't necessarily have to be a product of the brain, but it could be something irreducible that only correlates with the brain. It can be concluded that calculations on the basis of the Heisenberg uncertainty principle show that the probabilistic emission of a vesicle from the presynaptic vesicular grid could conceivably be modified by a mental intention, acting analogously to a quantal probability field. All that we can surmise is that mental events, acting as a field in the manner postulated by Margenau, could affect changes in the spatiotemporal activity of a module by changing the probability of emission in many thousands of active synapses. There need to be no violation of conservation laws. Basically, energy is not taken away or added. All that is changed is the mind acts to affect the probability distribution within the brain. So quantum mind theory explains how the mind could affect the brain without being physical itself. Now notice Eccles doesn't say the mind is composed of quantum particles or is reducible to quantum processes. And I want to be clear, we're not arguing for the idea consciousness emerges from quantum mechanics or is a product of quantum collapse. However, if irreducible minds do exist that are correlated with the brain, in order to retain our intuitive understanding of how our free will and other mental processes work, the mind, when manifesting in reality to cause real physical changes, would have to behave quantum-like. In other words, irreducible minds would be expected to manifest with a quantum-like nature to avoid the determinism of classical physics, and to have the ability to freely think and process information. Quantum systems and minds seem to correlate in how they behave, as the model of quantum cognition shows. And this correlates perfectly with where the evidence in quantum mechanics is pointing us, with the issue known as the measurement problem. Physicist Henry Stapp reminds us, the logical situation in quantum theory is there is an absolute logical need for something else, such as consciousness. In quantum mechanics, there is no physical equation to explain quantum collapse. Yet Stapp and other physicists have argued this measurement problem implies something beyond the physical descriptions and equations to cause quantum collapse, which they argue would need to be consciousness. Basically, all physical systems are bound to the rules of quantum mechanics. But quantum mechanics shows us no physical system has definite properties prior to being measured by an outside source. If all things physical are bound to these rules of quantum mechanics, this implies something outside the whole physical system must interact and cause collapse for the classical physical world to emerge as is. which points to the theory consciousness is what is interacting with the physical to cause collapse, instead of consciousness being an emergent feature of matter. Bruce Rosenblum and Fred Kuttner say, only a consciousness, something beyond Schrödinger equation evolution, can collapse a wave function. John Gribben and Paul Davies say, the observer plays a key role in deciding the outcome of the quantum measurements. Now, if the brain engages in quantum computation, then the same quantum rules and effects apply, so the implications of the measurement problem apply to the brain as well. If the brain has several different pathways along its microtubules in a quantum superposition, then what is causing measurement and final collapse? As we said, there is no physical equation to describe collapse. Yet collapse must happen for brain processes to move forward. The implication we see in quantum experiments would carry over into quantum biology. The wave function of the material brain is collapsed by the mind, or the observer. In other words, the mind measures the brain and produces real effects carried out in the brain. Thus, the brain itself would have in its very fabric the need for an observer to cause collapse, which would point back to the existence of an irreducible mind beyond mere brain chemistry. On top of that, this data correlates to what we see in the neuroscientific research on mindful attention and the plasticity of the brain. The mind is able to produce real observable effects in the brain, as researchers have pointed out in multiple studies. Thus, the evidence demonstrates the mind seems to be a real active force that collapses the quantum nature of the brain to produce real changes and cause results. Quantum biology and the measurement problem point back to an irreducible mind, not created by brain chemistry, that is needed to measure the quantum superpositions of the brain and cause actions to play out. Thus, quantum mind theory points to an irreducible conscious agent.